So last time I recorded a video. You may have not watched it, but I recorded a video where I went through the steps to create an element stiffness matrix for a triangle element for a plane elasticity problem. And so I'm just going to quickly go over assembly, because assembly is a little bit different now that we have 2 degrees of freedom per node, right? So if we have 2 elements and the local, so this will be element 1 and this will be element 2, and the local element node numbering scheme will be consistent with the one I derived, or the example problem I worked, 2, 3. And when I say example problem I worked, remember I didn't do that in class. I recorded and posted a video, so you may not have watched it yet, but it's there. And of course, we know that node numbering matters. So if I want element 1 and element 2 to have the same element stiffness matrices, I can't just number them arbitrarily locally. I have to number them in a smart way, and the way to do it would be to number it 1, 2, 3. So in other words, I can't just start in the lower left corner and go around, or I'll have a different stiffness matrix if I do that, right? So let's look at how we'd assemble this guy right here. So if you watch the video, you'll see that we end up with an element stiffness matrix for the triangle that looks like this, where this is for elasticity problem. So A and B are the length and height of the, well, A is the, so I should draw it on here. This distance is A. This distance is B. And it's a 2D problem, but through the thickness, then there's a distance H, right? And the C11, C12, C21, C22, C66 are the elastic constants that will be different depending on if it's a plane strain or a plane stress problem. Okay? But anyway, this is the element stiffness matrix. So we need to assemble it, okay? Well, if we go back over here, we can create a connectivity array that would be, well, I need to give some global node numbers. So like if this is the global node 1, 2, 3, 4, then my connectivity array would be 1, 2, 4, 4, 3, 1. Right, so we covered connectivity arrays in the video where we did 2D scalar fields, right? So this is the mapping between, that was a video, so I wasn't here to answer any questions. Does anybody have any questions about this, right? This is the mapping between the local and the global node numbers for each element, right? So if the first row is the first element, local node 1 corresponds to global node 1. So it's in the first entry. Local node 2 corresponds to global node 2, second entry. Local node 3 corresponds to global node 4, third entry. Same thing for the other element, right? So now we have 4, 3, 1. Okay? So there's our connectivity array. Of course, we also have some sort of degree of freedom map, right? So node 1 has degrees of freedom 1 and 2. Node 2 has degrees of freedom 3, 4. Node 3, these are global node, 5, 6, 7, 8, right? So ultimately, if we assemble those 2 elements, we're going to have an 8x8 global stiffness matrix, right? And so node 1 has x and y, which will map to 1 and 2. Node 2 has x and y, which will map to 3 and 4, and so on, right? Yeah. Yes. Yeah. So in this way, and in general, there's no optimal way to do it. But yeah, there are, based on graph theory and other things, you can come up with better node numbering schemes. In other words, I could switch around the local node numbers so that my connectivity array is different, and that would give me a better sparsity structure in the matrix. And yes, that is important, and it can speed up the convergence of iterative solvers. But then also there's a trade-off between, it takes some time to do that. Of course, it's usually something you just do up front, just once right up front. But there is some time associated with it. Yeah, and then of course in this case, the reason I picked the numbers the way I did, it's certainly not for the optimal sparsity pattern. You'll see it looks weird. I just didn't want to derive two stiffness matrices, or I just wanted to use the same element stiffness matrix for both. So that's really why I chose to number it that way. All right, so if we go back over here and create those arrays, the connectivity array, so we'll have connect. Can you guys see that? 1, 2, 4, 4, 3, 1. And then for the degree of freedom map, I'll just make a table to do that for me. So since they're consecutively numbered. And I don't have a K yet, but the global stiffness matrix will just be, we'll just initialize it to a constant array of zeros that's 8 by 8. So, I need to skip by 2 to get what I want. So that's what I want for the degree of freedoms, all right? So then just so you can see how we can use the connectivity array to index into the degrees of freedom. So if I print out the degree of freedoms corresponding to the first element, which is the first entry in the connectivity array. Right. So these are the degrees of freedom, or the locations in the global stiffness matrix that correspond to those elements. So they start off in order because the local node numbers correspond 1 to 1 for 1 and 2. But then when we go to 4, and that corresponds to global degrees of freedom 7 and 8. Okay. So that's why we get this. Okay. So then, we have 2 elements. It would be easy enough to but I'll just go ahead and put them in a loop. So I'm just going to flatten this array like this. So I'm going to get rid of the groupings. So I'll just flatten the array here. And then instead of 1, we'll put in I, and then K. And there are 2 elements, so we'll go from 1 to 2. So there's my global. There's my global stiffness matrix. So a little bit hard to fit it all on the screen. Maybe if I shrink it down a little bit. There we go. So I know it's hard, you can't see all the entries, but in the video you'll be able to see them clearly. But you can see the sparsity structure is a little strange, right? I mean, ideally you'd want that thing to be as banded as possible, and you know, you could get it. Yeah, I mean, yeah, it's hard to do in 2 or 3 dimensions to get it optimal, right? In 1D, you just number them consecutively, and it's always optimal, right? You always get a tridiagonal matrix.
After, like, if we number them like a triangle, like 1, 2, 3, 4, 5, 6, like this, so you can use the bandwidth.
Mm-hmm.
So like 1, 2, 3,
Yeah.
and then like 2. You can, I mean, instead of just if it was like a rectangular.
Yeah, if it was regular, yeah.
Yeah.
But in general, you know, your meshes aren't regular, so it's hard to do. So. I mean, normally, this connectivity rig, it also just comes from your mesh program. And in fact, on the next assignment, that's what I'm going to do. I'm going to just give you guys a mesh that comes from, you know, a qubit essentially, and then, well, I create the mesh in qubit. I'll give you the XYZ locations and the connectivity arrays that come from there. I'm not going to make them myself because I'm going to have hundreds of elements in it. So you can use qubit, or qubit is a Sandia program. I think the commercial version is called Trellis, but there's also many other mesh programs. HyperMesh, Gmesh is a free version, but yeah. So there's a lot of tools you can use. You can even just use Abacus or ANSYS and export. You know, even if you want to do the analysis in a different program, you can use the meshing tools in there. Yeah. Do what?
That's good. They have nice sketching.
Oh yeah, yeah. I like Qubit because you can script it, right? Qubit, you can drive it with they have this sort of own internal commands, or you can drive it with Python. So you can script it in parametric and make everything parametric. So you can, you know, you can put it in a loop and create 10,000 meshes at once. With, you know, if you were doing some kind of sensitivity study or something like that, right? So that's why I like Qubit.